Hey everyone, for this video I wanted to go over a couple of the select problems that we had from Chapter 4, and specifically this one is going to be about the source transformation problems. Now, much of the time with many problems, even if they're involving superposition, we actually end up using source transformation as a tool because, as we have discussed in class, source transformation is just a way for us to manipulate the circuit into a manner that we can actually solve in a more efficient way without having to use any type of systematic process like loop analysis or even nodal analysis. So 4.22 and 4.26 were great problems just to illustrate those points. But if we actually look at source transformation examples that we can utilize for 4.22, this really goes back to the special consideration paper that I put together for you guys. So make sure you go back and review that in addition to listening to this lecture on these problems specifically. For this problem, we actually performed source transformation not once but twice. But remember, for 4.22, we're looking for the current through IX. We're looking for IX through the 4 ohm resistor. And due to that notion, we can actually go ahead and perform source transformation maybe multiple times in order to actually gain the circuit into such a way that we can solve for IX very, very simplistically. But we're not actually manipulating 4 ohms or even its position within the circuit. So as long as we perform source transformation in an appropriate manner, then it really, really will help the problem become very, very simplistic. Now, again, just as a reminder, source transformation is really the operation of taking a voltage source in series with a resistance and converting that into a current source that's actually in parallel with that same resistance. Or conversely, taking the current source in parallel with the resistance and converting that into a voltage source in series with that resistance. So let's consider first the first source transformation that we could actually do for this problem. So as of right now, we can see that there's no way we could actually break down the circuit in order to find IX. So as right now, we would have to actually perform nodal analysis in order to actually find IX or even loop analysis. So let's go ahead and start stepping through some of the source transformations that we could do in order to actually get the circuit into such a manner that we could actually solve for it very, very simplistically, as we will at the end of this problem. So the first thing that we want to do is take the 2 amp current source in parallel with the 5 ohm resistor, and let's convert that into a voltage source that's in series with that 5 ohm resistor. So if we go ahead and convert that, we get 10 volts. Now here we got 2 amps multiplied by 5 ohms, and that converts down into a 10 volt source. Note the polarity though of that 10 volt source. The current source is actually pointing downwards, which means that current would leave downwards by the pointing of that direction of that arrow. But by passive sign convention, we have to make sure that that polarity is orientated in such a way that that current would be leaving the positive terminal of our voltage source. So therefore we put the 5 ohm resistor in series, and that causes the other 5 ohm resistor to also become in series here. Now, as we are looking at the circuit, it's still not in a manner that we could actually utilize anything other than KCL, essentially. We could utilize KCL and quickly come up with one equation, one unknown for this, which would be totally permissible. But if we actually perform source transformation again on this voltage source in series with the 2 resistances, then we may actually cause the current source and the equivalent resistance to become in parallel with that 4 ohms. And same for over here with this 20 volt source in series with the 10 ohm resistor. If we go ahead and convert that into a current source, then as we can actually see over here, all elements would therefore become in parallel. And once they are in parallel, we could easily find the total current that would actually be impacted upon the system, and then actually go ahead and utilize current division, and we're done. But either way is actually permissible to utilize KCL equations for this problem, or just go ahead and convert into something that we could easily just utilize current division for. So we take the 10 volt source. Now because the positive terminal is down, we would have to actually ensure that 10 volts divided by 5 plus 5, which gives us 1 amp. That current source is pointing down because the positive terminal of the voltage source is pointing down. Then we put that current source in parallel with the 10 ohm resistor. Over here with the 20 volt source in series with the 10 ohm resistor. All we have to do is take 20 volts, divide that by 10 ohms. That gives us 2 amps. Current source is pointing upwards because here the positive terminal of that voltage source is up. So we want to make sure the current source is oriented upwards. Now we take the 10 ohm resistor and we put that in parallel with a current source. Once we do that, all elements are actually in parallel. And just as we saw back in chapter 2, all we have to do is be able to note that with 1 amp pointing downwards and 2 amps pointing upwards, the total current that would actually be impacted upon the system would actually be 1 amp total, or 2 amps minus 1 amp. So all we have to do, because we have 3 elements in parallel, remember current division only works for 2 elements in parallel. So all we do is take 10 ohms and 10 ohms, put those together in parallel for their equivalents. So 10 ohms in parallel with 10, which is obviously just 5, over 5 plus 4. Remember, with current division, we put the opposite resistance in the numerator. So here we actually go through 1 amp, and then with this proportion as we have through current division, renders a final current value flowing through that 4 ohm resistor of 0.56 amps. And if we actually went through and applied nodal analysis or even loop analysis with this problem, we would actually come up with a total current of 0.56 amps. But we didn't have to use systematic equations. We could easily just go ahead and manipulate the circuit into such a form that we can actually just utilize current division. Now, for 4.22, we're going to take the camera and we're going to maneuver down that way. Dip, 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 dip. And this one is actually quite a simplistic problem to deal with, because even though we have 3 sources in this problem, it's very easy to see that if we look here, now remember with source transformation, we performed this technique in order to make the circuit more simplistic to solve. So if we look up here, if we took 4 ohms in series with 20 volts and converted that into a current source in parallel, then we would actually create another loop. So instead of having 3 independent loops within the circuit, we would actually have 4. And I've actually seen people do that on a test and then apply systematic equations. Yes, if you got it right, and I have actually seen students get that right, then, obviously it's permissible. But remember, the entire point of this analysis technique is to manipulate the circuits in such a way that we can actually simplistically solve it, not make more work for ourselves. I don't know, some people may like more work. That's okay. But sometimes I do. But in this case, I'd rather solve the system in a more simplistic fashion. I like this problem because just like 4.22, we can actually convert multiple sources within the circuit. And if we look here, we have 6 amps in parallel with 2 ohms. If we multiply those 2 together, we get 12 volts. Positive terminal is once again on top because the arrow is pointing upwards. So we would actually take that 12 volts, put that in series with 2 ohms. And if we look here, we could actually take 3 amps, multiply that by 5 ohms, and that actually would render us 15 volts here, where the positive terminal is in the direction of the arrow of the current source. So positive terminal is actually on the right, and therefore we would actually take the 5 ohm resistor, put it in series, and by doing that, we actually caused one single closed loop. So we actually broke down the circuit from 3 loops all the way down to 1 single loop. And from here, to find I naught, all we have to do is stay consistent with this arrow and go around the closed loop and apply KVL and also Ohm's law. So that's exactly what we had to do. V is equal to I naught times the equivalent resistance in series. So here we go around the closed loop. 20 volts here, that goes, current's going into the positive terminal, that represents a drop, so negative 20 volts. Go around the closed loop, we go from negative to positive, that gives us a positive 12 volts. And then with a 15 volt source, we go negative to positive. Once again, a positive voltage of 15 volts. and that's equal to I naught times 2 plus 5 plus 4. Divide through and solve for I naught. Bam, 0.636 amps. So guys, these two problems are good ones for actually understanding how to do source transformation. Please look through the practice exam because those problems actually will help you understand source transformation a little bit more. As usual, if you guys got questions, please contact me.